Okay.
All yours, Ian.
Okay, great. So, so the title of the talk is work done at the University of Toronto by Keith Party's group, and it's titled Point of Care Detection for Viral and Bacterial Pathogens using a glucose meter interface. Did the slide advance? Yeah. Did the slide advance?
Yes, it did.
Okay, good. Sorry. So point of care test sacrifice accuracy for speed and convenience. So basically, what we're trying to develop here is a point of care diagnostic that it's really going to enable rapid response to point of care diagnosis enables rapid response to infections. That's the sort of problem we're trying to overcome. Specifically in the technology field, the issues there with these point of care tests are that a lot of times they have a lot of high failure rates, such as false positives. You can't set up point of care things for certain analytes that you're kind of going after certain things, and so they're not very flexible. As well as, although it's possible to sample from a patient at the site where they are, the processing of those samples, in some cases, in classical sense, requires them sent off to labs and require quite a lot of delays in actually processing the sample, whether it's done on site or in a lab somewhere else. And more importantly, the analysis actually often requires very expensive readers and technologies that really make the analysis quite expensive. And so what we tried to do or the Party Lab is trying to do is to adapt something that's used ubiquitously in society right now, a glucose-based meter, people, and to use the way that reads out that as a readout. So we've adapted our technology to sort of use this very easy point of care diagnostic that is very easy to use and is ubiquitous in the space. So the next slide is, okay, there we go. So basically, the glucometer for detection of infectious disease, basically we could take a whole range of samples that come from whole humans or whatnot, but in this case I'm just picking animal health because that's the area we're kind of focused on right now. So you could sample things from various livestock, horses, or companions, but basically you get a sample prep, whether it's saliva, a blood sample, or some other form of sample. It's going to require a sample prep step. The sample prep will contain the genetic element, so RNA from a pathogen, for example. And basically, what we do is we lyse the sample up so that we expose the genetic element, and then we amplify it isothermically using standard kits and they can be purchased or integrated into our sample flow. And the step, generally speaking, for the collection and the application step is usually about an hour. Then we put on the core of our technology is the gene circuit, which is basically a readout where when it detects the RNA or the genetic element, it creates a reporter protein. That reporter protein then is converted to glucose by the glucose meter, and you get an output. And so basically what our sample, the isothermal application step gives you very high sensitivity. We get down to low attomolar detection limits of a pathogen in a sample. And the gene circuit allows selectivity. We can actually create gene circuits which provide the protein readouts for a whole variety of diseases. And basically you could take what we're doing is then if we compare it to a whole bunch of other tests, so the PCR tests, which are done where you can take sample tests people, they generally have very high accuracy. The processing time takes several days, however. The costs are very high, so $100 to $200 per sample per test. Rapid antigen tests, as we all know, maybe exposed to COVID, we've all done it. They have a very low accuracy, but they're relatively quick, and they are also low cost. The glucometer test has got very high accuracy. We can do it in 2 hours. The amplification step takes about an hour, and the readout and the gene circuit step takes about an hour. So about 2 hours, maybe an hour and a half. It can be done so it can be done definitely on site and get a readout very quickly. And the cost is pretty low. We're estimating our sample cost will be $10 per test. So the initial market, well, we've actually gone over some disease markets with typhoid, and I'll talk about that a little bit. But the market we're kind of going after right now, we're trying to expand into is animal health, and so we can look at the pets or equine or high value cattle markets where we can kind of where you could take it out to the farm and do tests on a wide variety of herd animals, for instance. The end user would be a veterinary or clinical staff can take it out and do a whole things, or a technician can kind of come out. The animal diagnostic space is actually pretty large. It's about a $4 billion market. It's growing quite rapidly, about 8% a year. The pet population is obviously, there's about $72 million in annually, and there's about 7% growth. So that's also high growth. People are starting to do more work with their pets for very custom work. They tend to care about their pets quite a lot. And then point of care testing, as basically the global market is generally expanded, again, is $1 billion and expanding about 8% a year. So it's a large and growing market. It's expanding. So there's space we can kind of grow into on this. So the status of the technologies, we've recently published a paper in 2021 where we applied our technology to the typhoid, and we had some pretty good results. And we've also started to expand our work into SARS-CoV. It's a very crowded space. There's so many tests out there right now. It's a very difficult market to penetrate, but the technology does work in that space as well. But what we're really looking at is to go into a market that's sort of uncaptured. And we've got a marketing reports for the NSERC, which have allowed us to sort of position our technology. What we're looking at really is mastitis detection in dairy cows. That's a big problem there, and so we're developing the test. So basically, we're optimizing the gene circuit elements for that, as well as the sample prep steps. And in collaboration with the NRC, we're actually now getting funding to build a prototype. The prototype would house a lot of the sample steps. So basically, you cut the sample and you take a portable unit, take it out to the site where the samples can be processed. It only takes a couple of microliters, not very many, like certainly less than a couple hundred microliters of samples used to get a readout. At the end of it, you get the readout from the gene circuit, and then that's just, you just can basically load that onto the glucose meter to get your readout. And you can multiplex this as well, or you could just do it sequentially, but you could do a large number of samples within a relatively short period of time. The IP status, we've got national phase patents are actually, we're working on Brazil, Canada, China, Europe, Japan, Korea, and the United States. We've got pretty good global coverage for this technology, because we see a lot of applications in addition to the animal health. We can go into a whole bunch of other disease areas that have unmet needs. The team is a very well-seasoned team, but Keith Pardee develops a lot of cutting-edge diagnostic technology at the University of Toronto. He's got his team with him, two postdoctoral fellows and a research associate. They're all kind of working and developing the technology, especially in the prototype of the sample prep module. So I think, and so the contact information here is just I'm sort of the commercialization manager here for the technology at the University of Toronto. You can contact us as well. We can put you in contact with our inventors at any time if anybody has any interest to learn a little bit more. But again, we're looking to develop the sample processing kit so that and the readout is already done. So we're trying to provide on-site solutions for a wide variety of diagnostic needs. Thank you.